everybody. I'm going to introduce you my seminar rates of cylindrical and spherical copper anode dissolving into concentrated sodium chloride water solution calculation using electrolysis and temperature increasing. I am a full professor at Rolf Ablazov East European University in Cherkasy town in Ukraine. And I am leading researcher at the State Scientific Research Institute of Armament and Military Equipment Testing and Certification in Cherkasy town in Ukraine. My article has been published recently in International Journal of Thermofluids. Overview. Michael Faraday's law of electrolysis. Some applications of electrolysis. Purification of metals, treating wastewater by electrocoagulation. Spontaneous mechanism of electrolytic dissociation of sodium chloride in water. Preparation of electrolyte, schemes of experiments, experimental results. Investigation at room temperature, investigation at temperature 100 degrees Celsius, unexpected results, the Arrhenius equation, discussion, mathematical modeling, conclusion. Michael Faraday's law of electrolysis. Michael Faraday, English physicist, has discovered law of electrolysis in 1830. Mass of metal precipitated on cathode is proportional to molar mass of metal, direct electric current value, time of electrolysis, and inverse proportional to charge of metal ions dissolved in electrolyte. F is the Faraday constant. F is approximately equal 96,500 coulomb per mole. Some applications of electrolysis. Purification of metals. For example, if we have copper anode and copper cathode, and the copper anode is not very pure, cathode is pure copper. So copper anode dissolves into electrolyte and pure copper precipitates on cathode. We can use as electrolyte copper SO4 solution. Treating wastewater by electrocoagulation. If we can use aluminum electrodes for treating wastewater. Aluminum hydroxide precipitates out from anode as colloidal suspended particles in an electrocoagulation system. The existence of aluminum OH3 serves as a coagulant to remove the heavy metal ions in the wastewater. Generally, copper electrodes and iron electrodes are used for wastewater purification. Svante August Arrhenius mechanism of electrolytic dissociation of rock salt, sodium chloride in water. In 1983, Arrhenius proposed a theory that when rock salt, which consists of sodium and chlorine, is dissolved in water, it splits into sodium atoms with positive electric charges and chlorine atoms with negative charges. These electrically charged ions, allow the solution to conduct electricity. Figures 1 and B show a schematic image of water molecule. Figures C and D show mechanism of the electrolytic dissociation of the electrolytic dissociation of rock salt, sodium chloride in water. Preparation of electrolyte. We have added sodium chloride in pure water and temperatures 20 degrees centigrade and 100 degrees Celsius. We have made concentrated sodium chloride solution. 5 mole per kilogram or 23%. Freezing point equals minus 22 degrees Celsius. pH equals about 7. The mass of sodium chloride dissolved in water at 100 degrees Celsius is a little bit more than at 20 degrees Celsius. Schemes of experiments. We have used copper cathode and copper anode. Copper anodes have cylindrical or spherical shape. Cylindrical anode degrades to thin rod, and spherical anode degrades to small ball. I is electric current direction, X is distance between electrodes, R is cylindrical or spherical anode radius, L is cylindrical anode length. Experimental results. Colors of concentrated sodium chloride solution in water during electrolysis with copper anodes and copper cathodes at temperature 100 degrees Celsius is are red, and at 20 degrees Celsius are yellow. Electric current value is I equals 5.5 ampere. Time equals 1 minute. And copper 1 chloride, copper 1 hydroxide, and a little quantity of copper 2 chloride and copper 2 hydroxide are formed at 20 degrees Celsius. Copper 2 chloride and copper 2 hydroxide approximately 60 weight %, and the copper 1 chloride and copper 1 hydroxide approximately 40 weight resents are formed at 100 degrees Celsius. Colors of the precipitates after electrolysis during 5 minutes. Temperature of the solution have not changed practically. Uh, so are shown at picture B. We can see yellow precipitate. Yellow precipitate is copper 1 hydroxide. Investigation at room temperature. Experiments were carried during 5, 10, 18, and 20 minutes. Rate of cylindrical copper anodes dissolving into concentrated sodium chloride water solution during electrolysis was in 2 times higher than the rates of aluminum or iron anodes. Chlorine gas was formed near the anode. Hydrogen gas was formed near the cathode. Investigation at temperature 100 degrees Celsius. Experiments were carried during 5, 10, and 20 minutes. Chlorine gas and boiling water were formed near anodes. Hydrogen gas and boiling water were formed near cathodes. We can see rates of cylindrical anodes degradation versus time. Copper, aluminum, and iron. Unexpected results. Rate of cylindrical copper anodes dissolving into concentrated sodium chloride water solution during electrolysis at 100 degrees Celsius was less than the rate at 20 degrees Celsius on 8%. This was first unexpected result. Rate of aluminum anodes dissolving during electrolysis at 100 degrees Celsius was higher than the rate at 20 degrees Celsius on 16%, as we expected. Rate of iron anodes dissolving during electrolysis at 100 degrees Celsius was practically the same as the rate at 20 degrees Celsius. This was second unexpected result. Electric current value increases with temperature increasing during electrolysis with aluminum electrodes, since general quantity of aluminum 3 plus ions increases too. General quantity of the hydrogen plus and chlorine minus ions decreases during electrolysis at all temperatures, since the chlorine and hydrogen gases are formed near electrodes. It decreases electric current value on approximately 1.3%. Electric current value increased with temperature increasing during electrolysis with copper electrodes. This was third unexpected result. The Arrhenius equation. Generally, temperature increases the rate of metal corrosion. Dependence of corrosion rate, CR, or weight loss of a metal per unit time on temperature could be expressed in the form of the Arrhenius equation as C equals A multiplies E in power minus E over RT. And for our experiments equals K P L rho. A is the per exponential factor, E is the activation energy, R is the gas constant, T is temperature, K is the metal cylindrical anode radius decrease in rate coefficient, L is anode layers immersed into the electrolyte at temperature of experiment, and rho is density of metal anode. It is exactly correct for aluminium, since it dissolves into an electrolyte as aluminium 3 plus ions. Discussion. General quantity of copper plus or copper 2 plus ions decreases with temperature increasing too. We guess that one reason only should be for electric current value increasing. Average charge of copper ions increases from plus 1 at room temperature to plus 1.5 at 100 degrees Celsius and to plus 2 at 180 degrees Celsius. While change of aluminium ions remains the same, plus 3. We have used law of electrolysis to calculate average ion charge. We have obtained for copper at temperature, at room temperature, it equals 1. For aluminium, it equals 3. And for iron, it equals 2. And at temperature 100 degrees Celsius, average charge of copper ions equals 1.5, for aluminium equals 3, for iron equals 2. So we can see that average charge of aluminium ions equals 3 at room temperature and at temperature 100 degrees Celsius. Average charge of ions equals 2 as at room temperature as at 100 degrees Celsius. Average charge of copper ions equals 1 at room temperature and equals 1.5 at temperature 100 degrees Celsius. Mathematical model. Electric current hits electrolyte during electrolysis due to applied external voltage if electrolyte volume is very small. We can use the equation of heat transfer balance. The electric current increases the electrolyte and container temperature, and at the same time the heat outflows into environment. U dt equals C glass M glass plus C electrolyte M electrolyte dt plus A out T minus TO dt. Here A out is the heat transfer coefficient into an environment. U equals 6 volts is applied voltage value between the anode and cathode. I equals 5.5 amperes. is the electric current value, T is time of experiment, T is electrolyte temperature, O is the environment temperature. C electrolyte is electrolyte specific heat capacity, C glass is the glass specific heat capacity, M is the electrolyte mass, rho is the electrolyte density, V is the electrolyte volume, and M is the glass mass. We can get the appropriate differential equation using equation 1. Integrating of equation 2 gives such equation, and such equation gives for this T equals TO plus BT minus BT squared over 2 T2 minus TO. Temperature of concentrated sodium chloride solution in water increased from 220 degrees Celsius to 60 degrees Celsius during 20 minutes of electrolysis. We can calculate using equation 4. And such T2 equals 206 degrees Celsius. And we can get finally function 6. Red dotted line shows heating rate in a thermostat, and the blue line demonstrates heating in a glass. We can see that experimental results are on blue lines. Rate of cylindrical anode dissolving into an electrolyte can be calculated using Faraday's law of electrolysis. This is differential equation. dm over dt equals mi over zf. Here m is anode mass dissolved into the electrolyte, t is the time of experiment, m is anode molar mass, I is direct electric current value, f is the Faraday constant, z is a charge of ions, a equals pr squared, is anode cross-section area, L is anode length immersed into the electrolyte, rho is anode density. Integrating of equation 8 gives for temperature increasing such result. Our experimental results show the copper ions average change value linearly depends on temperature from 20 degrees Celsius to 100 degrees Celsius. Our assumptions that from T equals 180 degrees Celsius and equals plus 2 in concentrated sodium chloride solution leads to linear dependence of the copper ions average charge value on temperature. Question 13. We have obtained an analytical solution for dissolving all the copper anodes finally. We can see that experimental results for the cylindrical anode are on blue line. If dissolving coefficient is variable, and depends on temperature, as in our case. If dissolving coefficient is constant and does not depend on temperature, we can see red line. Red line this is only for comparison, since such assumption is incorrect. But we can compare rate of anode degradation cylindrical and spherical shape. So cylindrical anode degradation we can see as a red line curve, and spherical anode degradation we can see as yellow curve. We can see that spherical shape effect is less than the cylindrical shape effect until t approximately equals 0.9 multiplies the dissociation. But it is enormously greater from t approximately equals 0.9 multiplies the dis to t equals the dis. 0.9. This is approximately 155 minutes. Summary. Increasing temperature leads to dissolution rate value of the copper anode decreasing, while electric current value increases, since average charge of the copper ions increases too. Such a result can be called as inverse Arrhenius law, so we can recommend to clear wastewater by electrocoagulation of copper cathodes and anodes at lower temperature. For example, 20 degrees Celsius. The dissolving rate value decreases approximately in 4 times due to the temperature increasing effect, while the dissolving rate value should increase all the time due to the cylindrical spherical shape effect. Dissolving time of spherical anode equals dissolving time of cylindrical anode if spherical shape is equal in volume to the rod shape. The spherical shape effect is less than the cylindrical shape effect until t approximately equals 0.9 this, but enormously greater from t equals 0.9 this to t equals this. Future investigation, for example, should include measuring of a wastewater temperature within electrodes during of electrocoagulation processes. Thank you for your attention. По тайму. Yes,
Что ты говоришь, хлоп или